Section 3.3, Power Functions and Polynomial Functions. We'll begin by identifying power functions. In a general sense, we have x as part of our base and an exponent. So like x squared, x to the third power, or a polynomial, or even something raised to a rational exponent. That would still be considered a power function. So by definition, a power function is a function that can be expressed in the form f of x equals x, k, which is a constant, times x raised to the p power, where k and p are real numbers, and k is known as a coefficient. Identify and behavior of power functions. This can be determined by the order of a function when written in standard form. So the end behavior is identified to the power. So an even power would be something that is like x squared, x to the fourth power, x to the sixth power, and so on, meaning my highest exponent is even. Odd power would be something like x cubed, x to the fifth power. That would be an odd power. Now, with even powers and with odd powers, there is some behavior to consider. So functions that are even power, those functions, their endpoints all end the same direction. So they both point up or they both point down. So the way we describe it, I like to say it in English, and then from there I can translate it into math a bit better. So I say something like my leftmost point points up, and my rightmost point points up. The way we say it is as x goes to negative infinity, the left side, we say that x goes to positive infinity, it goes up. So this is your left, and that's your up. The right side, the positive x side, so as x approaches positive infinity, f of x, your function, points up. X approaches positive infinity. This is if your constant, your leading constant coefficient is positive. Now, if your leading coefficient is negative, and you have an even function, your graph should both endpoints should be pointing down. So as your leftmost side is pointing downward and your rightmost side is pointing downward, we can say something like as x is approaching the negative x's, so negative infinity, your function is pointing down. It's approaching negative infinity. Same thing for the right side. The right axis, the positive side, as they get bigger, as they approach positive infinity, your graph, so your function, is opening down, so negative infinity. And that's what we have for our even functions. All right, I'm going to erase all of that so that we don't confuse it with our odd powers. So now looking at our odd powers. So same idea. If we have a positive leading coefficient and a negative leading coefficient, that affects our end behavior. So let's look at it. Let's look at an odd powered function with a positive leading coefficient. Our leftmost side should be pointing down, and our rightmost side should be pointing up. So using math, you would say something like as x approaches your negative, so negative infinity, your function is pointing down, so it's approaching negative infinity. Our rightmost side, so your positive x's, as x is approaching your positive numbers, positive infinity, your graph is pointing up, so reaches infinity. This, so we're doing right here is we're describing the end behavior. Describing end behavior lets us know how our graph is supposed to look. Similarly, if we have a negative leading coefficient, our leftmost point opens up and our rightmost point points down. So we can say something like, as x is approaching negative infinity, our function is approaching up infinity. And as x is approaching our positive number, so positive infinity, our function is approaching negative infinity. I like to think of left up and right up, or left down and right down, to help me keep track of what I'm trying to say. So with end behavior, it's determined by two things, the degree and the leading coefficient. So let's describe the end behavior of this graph. I have no idea how it's graphed or what it's supposed to look like. Well, we haven't covered that yet. But I can describe the end behavior because my exponent is even and there is no negative for a leading coefficient, thus it's a positive leading coefficient. I know that regardless of how it looks, my end behavior should both be pointing up. So I know my leftmost should be pointing up and my rightmost should be pointing up. Now we can write it in math. So as x is approaching negative infinity, your function is approaching positive infinity, so just infinity. And as your x's get bigger, as x is approaching positive infinity, your function is approaching up, so positive infinity. Describe the end behavior of the graph f of x equals x to the ninth. Again, we haven't talked about how to graph higher degree functions. I mean, yeah, we can always do a chart, but if I use my degree behavior, I know that this is an odd degree. 9 is an odd number, and there is no negative, so I have a positive leading coefficient. So we know our graph should be pointing. Again, I don't know what's going on, but I know the end behavior should be something like that. So I know my leftmost is pointing down, and my rightmost arrow is pointing up. How do we describe that? Well, the left is referring to our x's, and right here we have our negative x's. So as x is approaching the negatives, negative infinity, our graph, f of x, is pointing down. It's approaching negative infinity. As for the right, as my x's get bigger, my x's are approaching positive infinity or just infinity, and my graph is pointing up. So it's approaching infinity as well. Okay, let's define a polynomial function. Don't let this notation throw you off. Let's begin. Let n be a non-negative integer. A polynomial function is a function that can be written of the form f of x equals a sub n, x raised to the n power, plus dot 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 a sub 2 x squared plus a sub 1 x plus a sub 0. So what we're looking here is a polynomial. We're saying it can be any degree. The degree can be n. And no matter how many terms we have, we'll end up to where I have x, no x, just a number, and that's our polynomial. Think of something like x squared plus bx plus c, or quadratic. That's a polynomial. So this is just the formula. Don't let the notation, don't let it scare you. This is called the general form of a polynomial function. Each ai is a coefficient that can be any real number, but a sub n cannot equal 0. Each product of a's a sub I and xi is a term of the polynomial function. So your leading term is always your first term. Along with that, we have a leading coefficient. So if your first term, it's that number. The degree of the polynomial is the highest exponent, only if it's expanded out, where each term doesn't need to be multiplied any further. Sometimes you need to multiply it out. If you need to multiply it out, you can save some multiplication and just add up the exponents. So let's do this example. So this is supposed to be x squared. So negative 3x squared times x minus 1 times x plus 4. Determine the end behavior. Well, for the end behavior, I need two things. I need the degree and the leading coefficient. What you can do is you can go ahead and multiply everything out and multiply in the 3, and that will get you your expanded polynomial. That's one way of doing it. Another way is you can take your leading coefficient, unless there's something else that needs to be multiplied in. These are just ones. So my leading coefficient is negative 3. So all I need from that is that it's negative. And from there I need the degree. Well, that comes from the exponents. I have a square. This is degree 1. There's no other exponent. And degree 1. So if I add up my x's, this is degree 2 plus 1 plus 1. This is degree 4. And by looking at it this way, I can avoid multiplying it out. If you're unsure, if you'd rather be more confident about what you're seeing, you can always multiply it out. I know that's something I would do if I was in a quiz or exam, just to be extra, extra sure. So I know I have an even degree and the leading coefficient's negative. So I don't know how to graph this, but I know that my leftmost and my rightmost are going to be pointing down. So we say, as x is approaching negative infinity, my function is approaching negative infinity. And as x is approaching positive infinity, the right side, it's pointing down, so your function is approaching negative infinity. Intercepts and turning points of polynomial functions. Just like a line, we can also find the intercepts, which are 2 points that cross or touch the x and y axis. Intercepts and turning points of polynomial functions. A turning point of a graph is a point at which the graph changes direction from increasing to decreasing to increasing. So what that means is increasing to decreasing to increasing. The y-intercept is a point at which the function has an input value of 0. The x-intercept points at which the output value is 0. So your x and y-intercepts is, we have our x-axis. If a point were to touch our x-axis, that would be an x-intercept. You can have one or more than one. Similarly, if I have a point that touches our y-axis, those would be y-intercepts. To find your y-intercept, let x equal 0 and plug in a 0 for x. To find your x-intercept, let y equal 0 and solve for x. So in another sense, you let the other letter be 0. Intercepts and turning points of polynomials. The polynomial degree, n, will have at most n x-intercepts and n minus 1 turning points. So if I have, for example, 3 x-intercepts, then we can say, based on this definition, that turning points would be n minus 1. So 3 minus 1, since that's our number of intercepts. So I would have at most 2 turning points. Our bullet points tell us that polynomial functions are continuous, meaning there's no break on the graph. So they're just curves like that, or a lot more steeper. It also has no sharp corners, thus making a smooth curve. So this would be something like you can see for a polynomial function. Let's do this example. Given the polynomial function f of x equals x minus 2, x plus 1, x minus 4, find the zeros. All right, when it's in factored form, I can just set each factor equal to 0, so that I have x minus 2 equals 0, that's our first one, x plus 1 equals 0, and x minus 4 equals 0. So factoring is ideal for sure. Okay, we want to get x by itself. So our first one, we get x equals 2. For our other factor, we want to get x by itself. We're left with x equals negative 1. And for our third, we're left with x equals 4. Okay, so this is when it's factored. When it's factored, that's your best friend because it makes the effort you have to do and the number of work and steps you do is much less. Next example. Given the polynomial function, f of x equals x to the 4th power minus 4x squared minus 45, find the zeros. Okay, so I know my zeros are my x-intercepts. So I need to solve for x so that I have 0 is equal to x to the 4th power minus 4x squared minus 45. Okay, well, we see that my exponents are 4 and 2. So I can factor this. Well, I can try for sure. Let's look at our numbers. What numbers multiply give me 45 but add to give me 4? 9 and 5 I think work. Where if I make 5 negative, so that I have 9 times negative 5, I get 45, but 9 plus negative 5, I get 4. Cool. So this factors to be, because I have a x to the 4th power, x squared minus 9, and x squared, well, that was a plus 9, minus 5. Okay, I can set each one equal to 0. So I have x squared plus 9 is equal to 0, and x squared minus 5 is equal to 0. Okay, so let's subtract 9, subtract 9. We're left with x squared equals negative 9. I take the square root of both sides. Remember, plus or minus. We're left with x is equal to plus or minus the square root of negative 9. Next one, we add 5 to both sides. We're left with x squared equals 5. We take the square root to undo that square, so that we're left with x is equal to plus or minus the square root of 5. Alright, so we have our answers for x. X is equal to square root of negative 9 and negative square root of negative 9, square root of 5, and negative square root of 5. I can simplify the square root of 9s a bit further, right? Recall those i's. So I have I, and the square root of 9 is 3. So I have 3i, negative 3i. Ooh, that was a square root of 5, and negative square root of 5. And these are our answers. Last example. Given the graph, determine the least possible degree of the polynomial function. The least possible degree. So I have an odd function for sure because they point different directions. But looking at my zeros, I have 1 intercept, 2 intercepts, 3 intercepts. So the very smallest degree we can have is degree 3 because the x-intercepts give you a hint as to what the degree of your polynomial is. All right, so your homework is 13 through 43 odd. Sorry about that typo. All right, that's it for section 3.3, power functions and polynomial functions. Thank you.